Hello, Western. So, picking up from where we left off in the last video, I now want to come up with some kind of way to mathematically represent sinusoidal waves. So, as the name implies, we can write a sinusoidal wave using sine and cosine functions. Now, the thing to keep in mind about sine and cosine functions is that they have maximum and minimum values of plus or minus 1, and they repeat every 2 pi. So what we need to do is think about how you can stretch or compress the graph along the x and y axis so that it will have a maximum value equal to the amplitude and it'll repeat every wavelength. So starting with something simple, how do you stretch the graph sine of x along the y-axis so it has a maximum value equal to the amplitude? Well, of course, the way we do this is you can stretch any function by multiplying the entire function by a constant. So in our case, we want to write our function like this. Y is equal to a sine of x. So by multiplying the function sine of x by the amplitude a, I now have a function that has a maximum value of a. So now comes a bit of a trickier part. How do I stretch or compress a graph along the x-axis so that sine of x repeats every 2 pi instead of every wavelength? Now, if you remember back in your algebra class, you probably learned this a long time ago and haven't used it since, but you can stretch or compress graphs along the x-axis by multiplying the value x in the function by a constant. So here I give a little example of this. I have this dotted line here that's a function f of x, and the solid line is f of a of x. So everywhere in that function f of x, I multiply the x by a. And by doing that, I stretch the graph out along the x-axis. So we want our function to repeat every wavelength instead of every 2 pi. So sine of x repeats every 2 pi. Okay? So I want to multiply x by some constant. So we want to think about something like this. Say sine of k times x. And the question is what does k have to equal? Well, the point is that sine of x repeats every 2 pi. So sine of kx repeats when kx changes by 2 pi. So what I want is I want k times lambda to equal 2 pi. Because when x changes by lambda, I want the product k times x to change by 2 pi, so that my function repeats every wavelength instead of every 2 pi. So now, it's just simple algebra. If I solve for k, I see it's equal to 2 pi divided by lambda. Plugging this back in, I now have the function y is equal to a sine of 2 pi x divided by lambda. So this gives us the shape of the graph, but how do we describe a graph that's moving to the left or to the right? Well, again, if you remember back in your algebra class, we can shift a graph to the left or the right by taking the x inside the function and adding or subtracting a constant to it. So again, giving this example, I have a dashed line here which is f of x, and the solid line is f of x minus b. So it's important to remember when you subtract, the graph moves to the right. So if I want, say, a sinusoidal wave that's moving to the right with a velocity v, well, if we think about this, right, it's going to move by a distance that's equal to v times delta t. So I want to subtract v times delta t from x. So again, our previous function was a sine of 2 pi x over lambda. So now we have a sine of 2 pi x minus vt over lambda. And if we want to, we could rewrite this, because remember, v is equal to frequency times wavelength. So if I plug this formula into there, I have that my wave can also be written like this. A sine of 2 pi x divided by lambda minus 2 pi frequency times time. And so now, using this mathematical representation that we have here, we can start to describe all sorts of physical phenomena. So I'll leave this video here, and in the next video we'll begin to talk about the superposition principle, which explains what happens when two waves collide.